As we have seen, QFE has its limitations and is only useful in some instances. As pilots, we are not always interested in how high we are above the airfield. In some instances, we may wish to find out our altitude above mean sea level. This would tell us our elevation from mean sea level. This can be valuable, since terrain and obstacles are also shown as elevations from sea level. It would make our clearance of obstacles much simpler to calculate. However, in order to do this, we would have to insert the pressure value found at sea level into the subscale on the altimeter. If you remember from the lesson on pressure, we saw that the QFF was indeed a sea level pressure value. Surely, if we could insert the QFF value into the subscale, the altimeter would read our elevation above mean sea level. However, there is a problem with using QFF in altimetry. In calculating the pressure at sea level from any given location, QFF takes account of the effect that the prevailing temperature has on the pressure lapse rate. Indeed, this is vital in order that we can accurately calculate sea level pressure to produce charts. This is where we have a problem. The altimeter works on a pressure lapse rate according to ISA. It has no idea that temperature deviations from ISA will cause a varying pressure lapse rate. It has been specifically calibrated to ISA. What we must do is calculate the sea level pressure from a location using a standard atmosphere. This is known as QNH. However, QNH will never actually measure the true sea level pressure unless we have a completely standard atmosphere. QFF will always provide a more accurate sea level pressure. Let's work through a few examples of how QFF and QNH will differ under different atmospheric conditions. In this first example, let's assume that we have a station pressure of 920 hectopascals, 300 meters above mean sea level. The temperature at the airfield is minus 20 degrees Celsius. The airfield is obviously a lot colder than ISA. The pressure at sea level will obviously be much greater, but by how much? Let's work out QFF. In correcting the pressure to mean sea level, QFF will account for the fact that cold air will increase the pressure lapse rate. So QFF will read a higher value at sea level than normal. QNH will also work out the mean sea level pressure, but it will not know that the pressure lapse rate is greater because the air is colder. QNH assumes an ISA atmosphere, so QNH will not gain the same amount of pressure that QFF did. We cannot have two different pressures at one location. Since QFF is the most accurate method, we will assume the real sea level pressure to be that of the QFF. Because the QNH value is not as high as QFF, it will be found just above the real sea level. If QNH is set on the altimeter, and the aircraft is at the real mean sea level pressure, the altimeter will read below zero. Summarizing, we can see that at locations above mean sea level, in a colder than ISA atmosphere, QFF will be greater than QNH. Let's take a look at how we might calculate the sea level pressure when we're actually below sea level. In this example, let's say we're 50 meters below sea level with a station pressure of 1020 hectopascals and the outside temperature is 30 degrees Celsius. Since sea level is above us, it must be a lower value than 1020 hectopascals. The fact that warm air reduces the pressure lapse rate is recognized by QFF. The pressure is not reduced by much when calculating sea level pressure. QNH, on the other hand, does not know that conditions are warmer than ISA, and it uses a higher pressure lapse rate, reducing the pressure by much more. So, in 50 metres, to find the QFF, the pressure was reduced by a lot less than QNH. In this example, below sea level in warmer than ISA conditions, QFF was more than QNH. However, different pressures cannot exist at the same level. So since QFF is the most accurate, it will remain at the real mean sea level, and QNH pressure will be found slightly above mean sea level. Lastly, here is a summary diagram to show the relationship of QNH and QFF in all conditions. Even though QNH does not accurately measure sea level pressure unless the atmosphere is ISA, we have to use it as mean sea level because our altimeter is calibrated using ISA conditions. We will of course be in error, and later in this lesson we'll see how to calculate this error. From now on, let's assume that QNH is mean sea level pressure, even though we know otherwise. With QNH set on the subscale, the altimeter should read the elevation of the airfield when the aircraft is at the airfield reference point, elevation being the height above sea level. When we're flying, we refer to the indication of the altimeter as an altitude whenever QNH is set. QNH is more useful on cross-country flights because it provides a height above sea level, which is similar to the way our terrain is displayed on maps. There is only one problem with QNH. The calculated value of QNH was from an airfield pressure at a location. What happens if the pressure changes along our route? Pressure changes along our route creates quite significant problems. Looking at the diagram, we can see we have obtained a QNH of 1020 from the airfield and subsequently climbed to 270 feet. We shall maintain this indicated altitude all the way on our flight towards the airfield on the right. To maintain a constant indicated altitude, we would have to ensure that the pressure surrounding the altimeter will not change. To do this, we must in essence follow an isobar. If the QNH at our departure airfield was the same as at our destination, the isobars would be roughly parallel to the true horizontal. But look at what would happen to the isobars if the QNH was lower at the destination airfield. You can see that the isobars now slope towards the ground. En route to our destination, we must ensure our indicated altitude remains the same, but in doing so we're actually travelling closer and closer to the ground. So, our true altitude is getting less and less, but our indicated altitude is remaining the same. We have a saying to alert us to this problem. When flying from high to low, look out below. Our altimeter eventually overreads our true altitude. We can shorten the statement to be high, low, high. High to low, altimeter reads high. This is not a good situation if we can't see the ground. Unbeknown to us, we are actually descending in relation to our true altitude. Let's look at another situation. Watch what happens if the destination QNH is higher than our departure airfield. Notice that the isobars now slope upwards. If we were to maintain a constant indicated altitude, we would have to follow those isobars upwards. This time our true altitude is getting higher, but our indicated altitude is remaining the same. We can say then, from low to high, the altimeter reads low. Low, high, low. This situation is not too dangerous, since our true height is increasing, but nevertheless it's not accurate flying. What these principles show is the need to constantly adjust the pressure setting on the subscale to account for variations in horizontal pressure. Notice that the altimeter now reads a more correct altitude than before. This resetting of the subscale is a vital part of aircraft operations. When taking off or landing at an airfield, the controller will give us the correct QNH, which we must confirm we have understood by reading it back to him correctly. We must then adjust our subscale accordingly.
Golf Alpha Bravo Charlie Delta, 6 miles west, descending height 1,000 feet, request joining information.
Golf Charlie Delta, runway 02, QNH 1006, 3 aircraft in the circuit.
Runway 02, QNH 1006, Golf Charlie Delta.
This will ensure our altimeter is not only reading correctly, but is reading the same as other aircraft within the vicinity. However, this procedure only solves the error on departure or arrival at an airfield. En route, our altimeter would still be in error. How do we ensure that en route we have the most up-to-date pressure in the region in which we are flying? This problem is solved by the provision of regional pressure settings, called RPS. The map shown here allocates areas where RPS values are issued. These areas are known as altimeter setting regions, or ASRs. When flying into these various regions, the altimeter should be reset to the values provided by them. This will again ensure a more accurate altimeter reading, and also ensure everyone else is on the same pressure setting. However, even if we have the correct setting within a region, on approach to an airfield, the controller will still ask us to set the airfield's QNH, because it may be slightly different. The reason for this is that the RPS value is valid for 1 hour based on the lowest forecast QNH within the region. Our airfield will most probably have a slightly higher pressure value and be more up-to-date than the RPS value.